Welcome to the video on graphing polar equations. So you should have already seen polar coordinates and how those work and converting rectangular to polar and vice versa. And now we're going to look at polar equations and how those actually graph out. So I have a few graphs here to show you. Most of these are going to be of one type and a few names here. Limicons or limicons, one of the two, cardioids, and rose curves. So each of these has a name. You don't necessarily have to know which name goes with which curve, but we will throw some of those names out there as well. All of these plots are going to be of these types of equations. R is a plus b sine theta, or with cosine as well, a plus b cosine theta, or R is a times a sine of n theta, or a cosine n theta. So we're going to get those two types of curves for all of these guys, and depending on what the a and b are, will help us shape our curve. So I have a couple down here already. R is 1 plus sine theta, R is 1 plus cosine theta. You'll notice these are very similar graphs, but one is oriented along the y-axis, one is oriented along the x-axis with cosine. So these are always going to look similar, just a different orientation. So let me change this a value a little bit. So right now we have 1 plus sine theta. What happens if I change that? So now if I go to 2 plus sine theta, before, let me give you this name. This one is a cardioid. This is sort of the heart type shape that has that point right there in the middle. If I make this a 2 now, so now we get 2 plus sine theta. Now this is what's called a limicon. So this is a limicon. Doesn't have much of a dip right here, so there's no circle. It's not going in like it did before, but it's not quite a circle because it's sort of flat at the bottom. But this is called a limicon. So, and as the bigger I make that, the more like a circle it gets. It's still not quite a circle. There's a little bit of flatness, but the larger that a value gets, or more different that gets from this number in front of the sine theta, the b value, the more like a circle that's going to look. So by the time we get out to 4, that looks pretty much like a circle right there. If I go the other way, r equals sine theta, that is a circle right there of radius 1, because I don't have anything added in front. So r is sine theta, that's a circle radius 1. I can change this one r cosine theta, that's also a circle of radius 1, but this time along the x-axis. And then when I start getting values negative 1, negative 2, negative 3, that'll give me the same sort of shape. So these shapes are almost identical, depending on which way I want to go with those. Alright, so the real difference is going to come when I change this b value. So if I change this b value, I can start to get, there's just b is 0, so that's a circle centered at the origin, where the r is negative 2. If I change this now to, say, a 2 sine theta, we'll see another cardioid, but this time I go out 2 units in each direction on that axis. Now we start seeing this guy with a loop. So this is another limicon, but this is called a limicon with a loop because it has this loop in the middle. So once these have changed, different a and b value, I'll start to get these guys out again. And there's another one. So now the loop is a little bit bigger on that guy. And if I change my a, notice here negative 1 plus 4 sine theta, I just get a larger loop inside there as well. So all of these are going to be one of 3 types, either circles, limicons with a loop, limicons without a loop, or cardioids. So limicons, cardioids, and circles, those are going to be the main things that we get, and the limicons can be with a loop or without a loop. The closer these values are together, the a and the b, the closer those are, the less of a loop we're going to have. The more different they are, the bigger that loop gets. And I want you to notice a couple things. Here we have 4 sine theta and negative 1. Notice 4 plus 1 is 5, and that gives me this outermost edge, 5 right here. 4 minus 1 is 3. Notice that inner loop only goes to about 3. So sometimes there is a way to tell where exactly these are going to hit on certain axes. If I go ahead and look at, say, this cosine, negative 3 cosine theta, there's nothing added, so that's going to be a circle. It goes out negative 3 in the x direction. And here, if I do 2 minus 3 cosine theta, now we're going to get this limicon with a loop. Alright, so this guy with a loop, notice 2 minus 3, that's going to be -1. So we have -1 here for that inner loop. And then if I add the 2 and 3 add up to 5. And notice I'm coming out 5 in this negative direction here. So some of these, there is a pattern to these guys. When the cosine of 0, I get 2. Notice I cross 2 on the y-axis there. On this one, I'll cross the x-axis where that a value is, 1, -1 and 1. So there are lots of patterns that go on to these. Really, we're going to graph these on the calculator for the most part. So you don't necessarily have to memorize what happens if this is A, this is B, things like that. We will go over graphing by hand, but I just want you to notice the symmetry in these graphs. A lot of these are the same type of thing, just different shapes depending on those A and B values. Alright, let's move to this next type. So these are going to be the rose curves. Right now I have our sine theta, our cosine theta. If we make that A value out front bigger, notice that makes that circle bigger. Alright, so we're going to have a large circle to look at. So here we have r is 4 sine theta. Here r is 5 cosine theta. Let's make both of those 5. So now if I start changing the n value, the n is going to be multiplied by this angle right here. So let's go ahead and take that up to a 2. So 5 times the sine of 2 theta. Here I start to get what's called a rose with 4 petals. So this looks like a flower, 4 petals. Before I had a flower of just 1 petal, like with this cosine. But once I bump that up to 2, now I get 4 petals. If I take this n up to 3, now notice this one's going to be 3 petals right here. If I take it up to 4, now all of a sudden I got 1, 2, 3, 4, 5, 6, 7, 8 petals for 5 sine of 4 theta. Take it up to 5. This one has 5 petals in it. So with all of these, there's a certain pattern that goes on. With odd petals, I get exactly the same number of petals as I have that coefficient of my angle. So if this is a 1, I get 1 petal. A 3, I get 3 petals. I'm going to make that one a 3. At 5, I get 5 petals. So you can always tell how many petals you get just by this number you're multiplying by the theta. Also, if it's an even number, say 4, I'm going to get double the number of petals. So if it's an even number, like 4, now I get 8 petals. When it was 2, I had 4 petals. If we take this up to 6, now I get 12 petals all the way around. So these are always going to have the same type of pattern. Same number of petals as that coefficient in front of the theta. If it's an odd number, if it's an even number, then I'm going to get 2 times that coefficient for my number of petals. An interesting thing does happen. Notice also we're out a radius 5 in each of these petals. So from the center to the outside edge of each petal is always going to be this coefficient out front. So we go 5 units for all of these guys. Same thing over here, 5 units along each petal. And when I start to put in, say, non-integer values in front of this theta, so 9 theta over 2, I'll start to get overlapping petals. So this one is going to have overlapping petals. Let's take this one down to, say, 7 theta over 2. So notice each of these petals a little bit wider, but they still overlap. And this one has 16 petals. So 1, 2, 3, 4, 5, 6, 7, 8 on one side, 8 on the other side. That would be 16 petals for that one. But they do overlap. Okay, so all of these are going to overlap. 3 theta back to 3, 5 theta. Now this one, 1, 2, 3, 4, 5, 6, and another 6. So that's going to be 12 for that guy. So with these, you will get an increase in the number of petals the higher this number on top goes, or the larger that fraction is. And then the smaller that gets, the less number of petals. But you do get some overlap with these if you start throwing in fractions. We're not going to include petal count or anything on those type, but if you want to look for patterns, often there are patterns if you want to find them. So I encourage you to just play with some of these graphs. There's 11 pi over 2, so you'll notice there's a lot of petals on that one. we do get overlaps in the middle there. So these are what's called rose curves, as you might imagine. They remind you of a flower oftentimes, so that is the name where they get the rose curve from. Alright, so the next question is, how do I actually graph these things? So if I want to graph this, say by hand, how do I trace out a polar graph? Well, the way that we do this is we can get a little bit of help from the rectangular graph. So here's 4 cosine theta. So if I graph 4 cosine theta, I can go from 0 to pi and see what happens. So as that theta moves, notice what we get on the regular curve. So if I go to pi over 4, then this should be square root of 2 over 2 for the cosine of pi over 4, and then we'll multiply that by 4. That's the distance I'm going to go out right here. So that distance right there and this distance right here, those black arrows are the same length. You'll notice the scales are just a little different on the graphs. So treating this as a rectangular equation, you can still treat this r as a y like you normally would. Treat the theta as an x like you normally would. Graph it out. That'll tell you all these distances to go out along your angle. So notice I'm going from my angle 0 over here up towards pi over 2, and as we go towards pi over 2, that gradually gets closer and closer to a value of 0. Right, so that traces out a half circle right there. Once I get past that, now angles bigger than pi over 2, I'm still going to get the same angle, so I'm still along these rays over here, so say 3 pi over 4, but now I have negative values. So when r is negative, remember you go in the opposite direction. So here we're going in the opposite direction of that angle 3 pi over 4. And so this again is just going to trace out another circle as I go on toward that value of pi. Once I get to pi, I'm back around the edge of the circle, cosine starts to repeat, and I'm just going to keep going around and around and around. We'll do this for a couple more and give you an idea of how this works. So let's pick a different function. So let's try one of these limicons. Alright, so this is going to be one with a loop. So here we have 3 times cosine theta plus 0.5. You can think of that as 3 cosine theta plus 1.5 if you like. And we'll start back at 0 again. So if we start at 0, we'll notice we're 4 units up here on the x-axis. And so now we're going to start to trace that out. So tracing that out, we'll start to go around, and as we get closer and closer to this value down here where we cross the x-axis, you'll notice right there at 0, now our r is 0. We traced out sort of this, not quite a circle, but this curve shape that goes back around to 0 again. And then once we hit that angle, now we're going to have to start to go in the negative direction. So the closer we get down here to pi, I'm going to start taking all these values opposite of that polar ray that I'm on. So if I'm getting close to this value of pi, rather than tracing out in the pi direction, now I go directly opposite of that angle pi over here in my polar graph. And as this traces out, you just keep going around. So you notice this red line keeps going around. And let me play this one actually. I'll slow it down. Alright, so as this red line keeps going around and around and around, it'll just keep going around the circle. From 0 to 2 pi, then 4 pi, and 6 pi all the way around. But anytime that we get positive r's out of this, we're going to go in the same direction as the angle. Anytime negative, we'll go in the opposite direction, like in this case. So that's where some of these loops and things come into play, is where we start going in opposite directions from the angle that we're tracing out. And so then this comes right back around again, and just like the graphs repeat in rectangular coordinates, the graphs start to repeat in polar coordinates. So this again starts there, starts to trace out as we sweep through those angles. Let's try one more. So let me pause that, take it back to 0. So let's try maybe 2 more. Let's try a rose curve. All right, so here's a rose curve. This one has 4 cosine of 3 theta, so that's going to be 3 petals. And remember the graph of that, it's going to have an amplitude 4 and make 3 cycles. So if we start to look at something like this, let's see what happens. So this one is going to play. Alright, so we start at 0, start to trace out, and then notice right here I'm getting negative values. Okay, so a negative value right there for my r gives me going in the opposite direction on my polar graph. And as those things compute out, I'll just get this trace. So when it's positive, go in the same direction. When it's negative, go in the opposite direction. But this red line is just going to trace out from 0 to 2 pi, just like on this rectangular graph. So we're just plotting whatever r value we get. We'll just go either along the ray or opposite the ray as we go from 0 to 2 pi. So that's how this thing traces out. Let's speed this one up. Alright, so you can see it again. So as this goes out, it just makes this general shape right here. So you can watch it trace out when you do it on your calculator. And we'll cover calculator graphing in another video. Alright, one more here, just to give you an idea of how complicated these things can get. So this is not one of our standard curves. This is a butterfly curve. And you'll notice this is 1.5 times e to the sine theta minus 2 cosine 4 theta. So these graphs can get as complicated as you want. You don't have to stick with just simple graphs. You can throw in e to the power or natural logs or anything that you like in there. But with this one, here's what's going to happen. So we're going to start with theta, and as we trace around, notice I start negative, then it goes positive, a little bit smaller, positive again. Now we start to get negative direction, positive. But that angle is always just going between 0 and 2 pi. So it'll trace out this entire curve as we move from 0 to 2 pi. All right. And whatever r values I get over here, so you could use this to estimate what r is going to be, where to place these curves, sort of tell where these peaks and valleys are of where this graph is going to turn, what angle. So we can expect to turn at pi over 2. That was right there. Expect another one at pi, so that was this turn right here. So as this graph also has peaks and valleys, you'll also see turns along those angles for this graph over here. So hopefully that gives you a little bit of an idea of what these polar graphs can look like. There are many different types of polar graphs that have some very neat designs. So I encourage you to look through some more examples in the book too to see if you can find any more of these really weird shapes that sort of have this nice pattern of familiarity.